speaking loud enough? Is the audio good? Is it just, please let me know in case it's not. Okay, so we're going to talk today about visual displays of data. So I mentioned it earlier, it's super important that you know how to display the data that you have analyzed, but more important is actually that you understand graphs and that you understand how graphs can be deceiving and how graphs can actually be helpful. And so in the end of the day, if you will most likely, if you're not becoming a scientist or analyze your own data, which is possible, but what you certainly will do if you further your academic career, you will read papers. And when you read papers, you will see graphs. And when you see graphs, you will need to understand graphs. If you want to understand graphs, you need to know what can go wrong with graphs, what to pay attention to. So I personally think this is a super important class. And this is also what Nolan and Heinz are focusing on. So they basically talk about the positive and negative uses. So the positive use is that it can accurately and succinctly present information. So basically it can contain so much information. A really well-designed graph speaks more than words. You can, so those of you who will give presentations at one point in their time and show graphs and show data, you can spend easily on a slide where you have a graph on that contains a lot of information. You can speak 5 to 10 minutes just about that graph. There's so much to tell about a good and well-designed graph if you understand the inferences that can be drawn from that graph. So it's packed with information. It can reveal extremely complicated data, but unfortunately, that's also where the downside is. It can also conceal data. And that is unfortunately sometimes found in that way. So a graph that reveals a lot of data would be this example. That's a so-called COG-COM graph that basically shows as a modified pie chart quite a bit of information. And as opposed to a pie chart, which I'm not a big fan of, this is actually an interesting way to show data. So when you look at that, you have here data from April 1854 to March 1855. And it seems to be in Crimea, in Bulgaria, so somewhere in the east of Europe. And you basically see here death counts depicted as the length of the pie slice. What you have here, in addition to that, you have here a time series. And the time series is basically showing data as a function of time. So you have, if you start from April 1854, you go all the way around and you basically get to March 1855. So this is a time series, usually shown in a Cartesian format, not as a pie, but here shown as a pie. Good, and each of these slices basically shows you the death counts, and you see that here was a violent conflict. So you see this starting here in July 1854. Those of you with a history major may associate that, but there was a violent conflict that basically increased the proportion of people dying from wounds in battle. Consequently, also there was an increase in those dying from disease. Was unfortunately the bitter truth of war. It's not only affecting the soldiers, it's also affecting the general population, which has limited resources, basically lives in destroyed infrastructure, and basically an increase of diseases is quite commonly a side effect of war. And then you basically also had increases from other causes in the furthering of the year, which then also associated with an increase in the deaths from diseases, the more you got to winter. Because winter is in that region of the world quite brutal and quite cold. So you basically have an increase in the cause of death of disease. You still had a violent conflict, kind of like getting smaller as a proportion, and you had an increase of deaths from other causes. So now this is obviously a very sad statistic, but it's always important to understand the statistics and to know that there are different ways to depict different data. And so I think the graph, as far as I recall from Norton and Heinzen's captions, was created by Florence Nightingale to document these the occurrences during these violent conflicts. So that's one way to show and to convince people about the cruelties of war. Another example that Norton and Heinzen gives here is the most misleading graph ever published. So the Ithaca Times means to depict that the tuition at Cornell University has increased tremendously, whereas the ranking has changed as well. As we are being misled to believe, it has gone down, but it hasn't. And that's the last point. So we're getting to that. But there are basically four different things that are just totally off with that graph. And so it's like a graph like that should have not been published ever. So this essentially means to depict a time series. Problem number one with this time series is it starts at different times. So basically, we have here 1999 as the end date, and we have 1999 as the end date here. But it starts at different time points. Problem number one. So it's different time periods. Secondly, ordinal and scale observations compared on the y-axis. So if you think of a tuition, this is scale data. If you look at, if you think of a ranking, that is ordinal data. So this is combining this on a y-axis is inherently absolutely wrong. So you cannot do that, not in quantitative terms, right? Secondly, deceptive starting point on the y-axis. So now we know there's a deceptive starting point on the x-axis with the time periods being just absolutely off, not aligned. On the y-axis, you basically have the same issue. It's like, why is the ranking basically starting here, whereas the tuition starts here? And it's not even depicted what each y-axis could mean. And lastly, and that's my favorite, and that's the best, because basically you have tuition go up, which is debatably good, and then you have the ranking go down, which is good, right? Because you want to be on rank 1 and not on rank 8. So it's an implied meaning what they actually want to say, right? So you cannot depict an improvement of the ranking as a decrease in the numerical value. So that's why this just doesn't make any sense whatsoever. But again, this is just the starting ground for essentially what we will be discussing now, because there are different ways how to mislead with graphs. And Norton and Heinz put a lot of emphasis on that. And so I don't know the literature in the psychological world, but I believe them that it's the prime and most important thing to start with. So there are good ways to depict data and there are bad ways to depict data. And what's important for you is to understand what are these good ways, what are these bad ways, and how can you recognize them? What questions do you need to ask that graph, and what do you need to extract from that graph intellectually? So firstly, you have a biased scale line. That means that you skew the scale. And we have seen that just with the Ithaca Times graph, right? So you need to have a clear presentation of that scale. You need to show the data in reference to that scale, and you cannot play around or distort your data by distorting and manipulating your scale. Then you have a sneaky sample lie, which is essentially not only something pertaining to graphs, that's just generally data analysis. You need to include all data that is relevant to your graph, and you cannot kind of cherry pick whatever data you want to show. So the sneaky sample would create a selection bias, would distort and mislead by basically just picking those data that are favored to your purpose, to what you mean to show. So you can't do that. The interpolation and extrapolation, so okay, let's take the last one first. So the inaccurate values lie. So this is basically where we're back to the scaling. So you mean to imply a different meaning than what the data actually really shows. Interpolation and extrapolation, that's where I want to go on the next slide, because it's easier to show it on an actual time series. So you see here the crime rate in Quebec. You see the time and crime rates in Quebec increasing from 62 up until 97, and then a decrease from 97 downwards. So let's only focus here on the total crime. So we have extrapolation and interpolation. Inter means it's in between. Extra means it's outside. So the interpolation lie is a statement where I say from 1986 to 2006, the crime rate has decreased. If I take the Y value here and I go all the way down here, it has slightly decreased, right? But I am lying about what's happening in between, because there's actually a substantial increase here at around 97. And then the decrease only started. So there's something that happened here between 1986 and 97 as well. So this would be an example for an interpolation lie. An extrapolation lie would be that I say, like, from 2006 to 2010, there must be a decrease. So I'm extrapolating something where I don't have data presented. Or even worse, I continue the graph, like with a hypothetical trend. Don't do these hypothetical trends. So you can build models, you can build probabilistic models to kind of predict the trend to continue with a certain level of confidence, but you cannot make any true statements about how it developed beyond that data you have at your disposition. So that would be an extrapolation lie. So now, speaking about the distorting the scales and misleading by changing scales. When you look at this graph on the right, what you see, first of all, do never depict any graph with like little homunculi. That's just not okay. That's never okay. That's like a pictorial graph, and we will see an depiction later on that topic. That's just absolutely not okay. And it's just making the graph unnecessarily busy and just misleads in a whole different way. Also, when you look here at the 3 years from 2008 to 2010, you see a tremendous increase in the recruitment numbers, right? But it's not a tremendous increase because essentially it's less than 10%. But it makes, by changing the scales, you make it look like this grand increase, and you're misleading your reader without actually having any substantial support for that. So just make sure that you understand what it actually really shows, and that you understand the scale to which it's scaled to. Yes?
Would it be possible to do it in the opposite way? Does that also count as inaccurate values?
Well, that would even be worse, right? Wow. How do you mean? No, I'm trying to understand. What's your thought process?
Like making the scale smaller than it has to be in order to sort of prove your data.
Ah, that's a good one. Yeah, I like that. So because that's misleading in the other direction. Yeah. And you're absolutely right. Because if you, and this is where the art of graphing is, that you need to find ways to depict your data that is reliably reflecting what you actually want to show. Like here in that example, it's actually better to show a percentual increase rather than the actual numbers, because you have so tremendously large numbers. If you do from 0 to 47,500, you basically have like this huge graphs, and then you only see like the small change, right? That doesn't make any sense either. You need a percentual increase relative to the actual absolute numbers. Very good point. Thank you. Yeah. So there are definitely more favorable ways, better ways to depict this data. So yeah, very good point. Then we have scatter plots that basically depict relationships between two scale variables. Why do I want to show that? Why do I want to look at this data? Because in a lot of research questions, you're actually interested in a relationship between two variables. And that's actually a lot of the research that is being conducted uses this so-called correlational analysis. And we discussed it in our second module, chapter 1. We talked about correlational analysis and the between group comparisons. So scatter plots are classically used in correlational analysis because it shows the relationship between two variables. And so it does in this example. So we're having athletic performance as a function of exercise or deliberative practice, which means, and so let's assume there's a relationship. There is a relationship, but it's not the strongest relationship, but there is a relationship. And this relationship makes a lot of sense, right? If you want to get better in a sport, you need to practice that sport. The more you practice that sport, the better you get in that sport. Makes sense. So it's a positive relationship. It's labeled positive relationship. If you do something that makes something go down, so let's say your exam grades go down when you miss class more often, or the less hours you learn, that would be an inverse relationship. An inverse relationship that essentially is negative. So you talk about a positive or a negative or inverse relationship. So in positive, the y-axis, so always also keep in mind, the outcome, the dependent variable is always on the y-axis, whereas the independent variable is always on the x-axis. So you're talking about the y-axis, the dependent variable, as a function of your independent variable. So athletic performance increases as a function of number of hours exercised that sport. And these relationships, and now I'm going back to the previous slide, these relationships can have different shapes and forms. The one that we're dealing with are linear relationships. Linear relationships is like you fit a line through this, and this is how you describe that association. There are, in addition to that, there are also nonlinear relationships, and nonlinear relationships can be exponential with a curving towards the positive end, exponential increases. Then you have logarithmic relationships, where basically you have, I don't know who of you does chemistry, you must have learned about Michaelis-Menten. So you have a sharp increase that flattens out then, enzyme kinetics, typically logarithmic relationship. So you have a linear and non-linear relationship. You have scatter plots depicting that, and you can interpret these relationships into a scatter plot. And a scatter plot, as the number one rule in a scatter plot, each individual point is one subject. So this is student number 1, practiced 11,000 hours, has an athletic performance of 4. Student number 2, practiced 12,500 and has an athletic performance of 8. So it's basically each point is one subject, one individual, one patient, whatever you are studying. So when you want to create a scatter plot, and this is where Excel comes into play, so you basically need to first organize your data by participant, then you label your axis. That's important because you need to label them properly, also with the units. And you need to make sure that your axes are long and wide enough that they take the minimal and maximal entry. And they basically depict the entire range of available data. Then you label the y-axis, possible values, and you basically mark each individual point. This is where we're going now to Excel. And so I have added a small little spreadsheet. This is just basically playing around a little bit with data. So you have here A1 to A21. This is exactly that data that you have just seen from Nolan and Heinzen. So I have digitalized this data. If you select this data, and this is maybe, keep this in mind that we're doing this right now because you will need to do this for the homework. So basically, if you select A1 to B21, you basically go and insert And you have here somewhere here on the right, you have the graphs, the charts. If you go on one of those graphs, there's one that basically shows here a scatter plot. If you hover over it, it will show you XY scatter. Yes.
Could you zoom in a tiny bit?
Unfortunately, not in that aspect. I would hope so. But you can also go and recommend the chart. So if you just go over each of them, they will show you different. They will show you hierarchy. They will show you waterfall, combo, XY, and there's one XY scalar. You can also click on recommended chart, which is basically the first one on recommended chart will be the scatter plot, because it's just so typical data. So if you click on recommended chart, you do scatter plot, you get exactly this. And that's the same scatter plot that Nolan and Heinsten have shown. So if, so that's always the problem. So here I can zoom in, right? I can't zoom in on the ribbon. Okay, so you want to change the chart title. You see here, athletic performance. Athletic performance is a function of hours of exercise. And then you basically zoom back out. No, not this. You can always zoom out here. Yeah. Then you can add an axis title. So if you click on the graph, you have here on the very left top, you have add chart element. So you need to activate. Go away. So you have here on the right side, you have chart design and format. If you click on the graph, you have chart design and format. If you click on chart design, this will pop up. And you have here on the very left, you have add chart element. If you click on add chart element, it will give you here the menu point axis titles. On axis titles, you click on primary horizontal. Primary horizontal allows you to add here an axis title. And that's hours of exercise. So I mentioned, yes. Yes, just click on the chart. Click on the chart, make this go. Click on the chart, and here on the right, there should be chart design and format. Yeah, if you click on that, this should pop up, and you should have here on the left add chart element. If you can add chart element, you can select axis titles. If you don't have it, we need to look at it after class. So we have primary horizontal will allow for you to label the x-axis. And if you go at the very end, so you need to always add the units of measurement on the x-axis. I traditionally do this with brackets for that very reason, because it's part of the conventions of how to label units. You don't have to do it in brackets, but it's most commonly accepted to do it in brackets. If you click now back on the graph and you go on add chart element, you can go back to axis titles and you can do primary vertically. Primary vertically allows for you to label the y-axis, and here you do athletic performance. Athletic performance. All right. So this is the graph. This is the graph ready. And this is how quickly you can do an scatter plot. Okay. So this scatter plot is consistent with the scatter plot that Nolan and Heinzen showed. What you can do next is if you click on add chart element, you have here last, you have the label trend line. So you can fit an actual trend line through your scatter. If you click on linear, you basically get a linear function, a so-called line of best fit that is fit in that scatter that you have created in your graph. And this line of best fit is basically fit in that scatter that it minimizes the distance from each individual point. So it takes the entire population into account. It fits a line so that it minimizes for each individual data point the distance of the individual data point to the line. And this basically is the line of best fit, fitted using a method called least square estimation method. Because we will do this on Wednesday, we're calculating the standard deviations, we're calculating the squared deviations, which is basically the numerical difference between that point and the line to the power of 2. So that's a squared deviation. And it basically minimizes these squared deviations from the line to the individual data point, also called a residual, but that's too much. But we're basically, we're minimizing that, and we're using a least square estimation method for the line of best fit. Good. So this was that graph. We have now completed our first scatter plot. You will need that for the homework with some simple examples, not too complicated. We know how to do that now, and we know now that there are 3 different interpretations of your scatter plot. Number 1, there may be no relationship between those 2 parameters. What you essentially will see if you do an Excel the trend line and you have no relationship, you will see a flat line. That is literally no relationship at all. If you have a linear relationship, you will fit that line through that scatter quite well, and it will seem like a quite accurate estimate of that relationship. A nonlinear relationship is a curved relationship. It can be exponential, it can be logarithmic, so there are various ways how that can present. But know the difference, please. So, any questions on the relationships on the scatter plot? I think it's quite intuitive. We will discuss it more when we come to chapter 15 and chapter 16. We're going to talk about correlation and regression analysis. Off note, let's go back to the Excel spreadsheet. I want to quickly say that. If you have this trend line here and you double click the trend line, you have here an additional feature. You have here display equation on chart, and you have here display R² value on chart. If you click that, you basically get here a regression model, which is basically, and I am just letting you know, it is my expectation that you all know about a linear function and that you all know how the equation for a straight line is, which is basically depicting a y, which is on the y-axis as a function of the x, which contains a slope, which is the slope with an increase on x, and the intercept where this goes through the y-axis. So you should have learned that in high school. So this being said, this is what we will be doing in chapter 16. Maybe a little larger. So if we look now at this function, we see here 2 components. So we see here this line equation that basically shows y as a function of the x with slope plus the intercept, and we see an R². And the R², without going into much detail, because we will calculate all of this in chapter 16. So the R² is basically a reflection of how well that relationship actually presents. How good is that relationship? How good can a linear function actually describe this data? It's simplified. It's a little bit more complex than that, but that's basically what the R² is. And you can just quickly compute that by checking that one box. Good. But that was beyond the scope of this class, but we will revisit that later. Okay, line of, yes?
Is R a coefficient?
R is the correlation coefficient.
Right.
In a bivariate analysis, R² is the squared R. Yep, good point. It comes in the same direction, right? It goes in that. Okay, So next, we have also line graphs. So scatter plots are used to construct this line of best fit through that entire scatter. That does not mean that it's a line graph. There's a huge difference between a scatter plot and a line graph. And please know this difference. And if you construct a scatter plot, for some interesting reason, Excel would allow you to connect those dots. Please do never ever connect the dots on the scatter plot. They're independent observations, they're independent subjects, they're independent individuals. The only time you use a line graph, the only time, is when you have a y value, so a dependent variable that you're depicting as a function of time. When your x-axis, your independent variable is actually time. Then you're actually supposed to connect the points at each different occurrence on the x-axis in the respective value on the x-axis. So the example that Norna tries to show is time plots that show the mood changes on Twitter. And that's already one of these examples where you actually see how much information you can put on a graph. So this is a pretty loaded graph. There's a lot of information on that graph. And there's not only is the descriptive information on the graph, there's actually a lot of wiggle room for inferential statistics. So you have here color-coded, you have the different days of the week, which you have depicted here as a function of time. So each of these days reflects the course of an entire day and the activity on Twitter. So there was somebody who went through all the Twitter posts of a day and categorized them as per positive or negative attitude in the post. And what's interesting to see, because this is where inferential statistics start. So you have on Sunday, these are orange is Sunday. So you have here a sudden increase of positive attitudes on Sunday. Generally, Sunday is higher in positive emotion, but low on negative emotion because people are not working, right? So they're waking up sometime at like 7, 8, 9. At 9, they're waking up and they're happy and they're in a good mood. And then it goes down, they're still in good mood on Sunday evening. Then Monday starts. They're waking up and they're going to work and it's at the lowest. Tuesday, basically, their mood is the lowest. Positive emotions are really low. Negative emotions are sky high. So it's interesting to see that, right? And this is this is drawing inferences from data. It's like it's all speculative, right? It's all speculative, but you see this real world evidence reflected right in front of you. And it's a fun example, but it's such an obvious dynamic, right? It's in that context, and I told the other class about the same thing, is like you have Google Analytics. I don't know whether you heard of that, but this is like publicly accessible data where you can go into Google and you can find search queries for where is the closest pharmacy, and that spikes during the flu season in winter. Or where do you get sunscreen? That spikes in summer. So it's interesting what you can see based on the behavior of people in the internet. Yes, please.
What would be a case where you could combine this study with also using the scatter plot?
It's tricky because you're missing on the scatter plot, you're missing the temporal component. You have no time. What you could do, and I've done that. That's a good question. I like the question. So you want at the end of the day, you want to pack as much information into that graph as possible. What you could do, and it's tricky, it's programmatically tricky. You also would need to find a really good use case to do that. What you could do, and when you can combine line graphs with scatter plots, is so each of those is one measurement. So you had one student athlete at one point in time. if you have that student athlete 3 times in a row in a distance of a month, let's say, what you could do, you could depict the temporal component by connecting only these individual measurements of one athlete. And then you would see indirectly the temporal component, because you know the difference in between is 1 month, but you see how his time of practice changed and his athletic performance in conjunction with that. That would be one way to do that. It's not a norm. It's not a commonly found graph. I did it in the context of acute kidney injury and how a lab parameter changed with progression into disease. That was the context I used it. But it's not a straightforward analysis. It's not something that's commonly done. This is analytically, longitudinal analyses are just a different animal. So this is meant for one cross-sectional assessment, whereas the line graph is temporal. So, but good question. I like the question because it is something that there are use cases where you would do that. Yeah. Good. Next, bar graphs. So bar graphs is different. So essentially, we have discussed already bar graph. We have discussed histograms. Histograms basically define a certain range of values and counts the occurrence of that respective range of values. So if you have that range and 20 people give you that respective range, you count them and you depict them on the y-axis in that range. So the histogram shows this in an increasing magnitude of the numerical value. So that is a very specific bar graph. But we basically we can now look at data in a bar graph also in different contexts. So whenever you want to show a scaled variable on the y-axis as a function of a nominal or an ordinal variable, you would utilize a bar graph. If you rank them and order them according to the magnitude of the numerical value on the y-axis, you would get to what is labeled here Pareto chart. The example here that Norton and Heinzen gives is the percentage of internet users also use Twitter. So Twitter seems to be very popular in Indonesia, Brazil, and Venezuela. So you have them here in alphabetic order. That's a standard bar graph. That's the usual bar graph that Excel will give you, R will give you, SPSS will give you, whatever software you're using. If you want to reshape this in a Pareto graph, you just need to rank them and order them according to the magnitude of their value, either highest to lowest or lowest to highest. Both is a Pareto chart. It really depends why you would choose either or basically would be dependent on the use case and what you actually want to do with your data and what's the point that you want to make with your data. Yes.
I guess my question is really like, it seems like a Pareto chart is just so much more, it's just easier to read and seems to get your point across. Like, why would you use a standard bar graph? It's so messy for lack of better.
Well, again, it depends on the use case, right?
Well, can you give me an example of a case to use a standard bar graph instead of a Pareto chart?
So here you have nominal data. With nominal data, it's a little trickier. Let's imagine this to be all the countries of the world. That's like how much, like 280 and 220 countries. So you have like these long lists of data and you want to find them. It's just easier if they're alphabetically ordered. That would be an argument. That was a low-hanging fruit. Other example where you would not order them according to the magnitude. Let's say you have an ordinal variable. Let's say you have the happiness from 1 to 5. You don't want to order them according to the magnitude because then it becomes like a non-informative graph almost. So as I said, it depends on the use case. It depends what information do I want to convey to my audience. That determines the graph I'm choosing. A good question, thank you. Okay, bar graphs highlight differences between averages and percentages. So debatable example, the number of tattoos so people who have 4 or more tattoos are more likely to have at least one arrest. Yeah, I don't know what the meaning of that is, but you can again lie by playing around with the scale, by basically dropping one category, which is the last category is basically gunner, and by discontinuing the axis, you basically make it look like there's no relationship whatsoever, and that's just pure chance. Whereas the other one, the initial one, showed like a remarkable trend, which makes you believe, maybe there's something in there. Maybe there's some inference to draw there. Who knows? Yeah, if you deceive the scale, if you deceive with the scale and you discontinue the scale and you drop one category, the graph is absolutely different. It's a whole different message. It's a whole different interpretation. So that's really the message of this graph, of these two graphs. Pictorial graphs, yeah. So nowadays you can do a lot of different ways of depicting data. All of them are somewhat debatable. So again, the easier, the better. The simpler, the better. You want a graph, you show a graph. No color, no patterns, no vibrations, no whatsoever, whatever these add-ons are that make them visually more appealing. They may make them visually more appealing for the desires of a certain audience, but in the end of the day, they're not more informative, and if anything, they're misleading. So that also is true with distorting graphs, which just doesn't make any sense why I would show anything like that. Pie charts. Same problem with pie charts. Super popular graph. You see so many pie charts, like just don't do any pie charts. It's a terrible way of depicting data because it basically doesn't make it comparable. So let's assume, okay, the item you at least want to learn about the child at university seems to be inherently different between Democrats and Republicans. I don't know where the data is from. So if you had a farm animal in a dorm room, that was less concerning for Republicans than for Democrats. If you made fake IDs, and you see already when you want to compare that, that was concerning for 8% of Democrats. Okay, now, but if you do this comparison, you need to go after the color code, you need to compare, you need to look. It's like, if you do this in a bar chart and you show them right next to each other, you do the very same comparison in a fraction of the time it would take in a pie chart. So if you really want to extract value and information from that chart, you don't use a pie chart. And that's my point. Nolan and Heinz's point. So I personally, I hate pie charts. I don't do pie charts. And I think I have not ever been convinced that a pie chart would be a superior way of depicting data as compared to a bar chart. Okay. What's really one of the outcomes of this class is like I can show you whatever we are discussing in only so much detail. I can make you learn only as much, but what's really the take-home message of this class is I want you at the end of the year, of that semester, I want you to know which methods to use with what data and what research question, and I want you to know which data will have which corresponding graph. So I think these are, I'm trying to kind of create a scenario where it's really more about the overview rather than the details. And the money for this class is really on this slide, that you know what graph to use for what question that you mean to ask your data. So if you have one scale variable and you just want to understand the frequency and the frequency distribution, build a histogram or a frequency polygon. If you have one scale independent variable and a scale dependent variable, you build a scatter plot, or in the particular case, when the x-axis, the independent variable, is time, you build a line graph. If you have one nominal or ordinal independent variable and one scale dependent variable, you do a bar graph. Or if the use case points out there's advantage to order them and rank them, then I do a Pareto chart. Just look at the question, try to kind of envision the graph. So at the exam, you're looking at the question and it asks you, okay, which graph are you going to use? Look at the question, envision what that will look like, map it out, draw it if you want to, and just think about what would be the most appropriate graph. But this is really the slide you want to keep in mind. Okay, nominal, ordinal, independent variable, scale-dependent variable, and then 2 or more nominal or ordinal independent variables and 1 interval-dependent variable. Then you do a bar graph. Okay. All right. How to read a graph? And that's the next one. That's the take-home message. Is like, how do I look at the graph? And what am I really interested in? So firstly, understand what is the outcome variable. What is the dependent variable? What is that on the y-axis and why is it there? And why is that the dependent variable? Then you need to understand, is that dependent variable, is that variable on the y-axis, is that an ordinal, nominal, or scale variable? And if so, what are the units? What are the units of that variable? And then you move on slowly to the independent variable. You think of the independent variable. What kind of variable is that? Why is it predicting the dependent variable? What kind of variable is it? Is it ordinal, nominal, or scale? And what are the levels? And what are the units of this independent variable? All of these are really the most important take-home messages and the most important hallmarks of this particular graph. Any questions on that? I think it's logical. Just understand what you're looking at, right? It's like understand each variable, understand what it means and what this relationship could indicate. Guidelines for creating a graph, clear specific title, labeled axis, always labeled axis because otherwise nobody's going to know what you want to show. Include the units. By all means, always include the units. Use the same language, use the same terminology in the title, on the graph, in the caption. It needs to, because in the text, use the same labels. Otherwise, you're confusing your reader. And you will find a lot of papers actually where this is violated. Anecdotal is like you will find a lot. So it's kind of interesting. Make the values from 0 to Katma, from 0 to the highest value at least. Don't conceal any data points. If you need, make cut marks, discontinue the axis, but make sure to make like a big red exclamation mark and indicate it to your reader that they know it, not really an exclamation mark, but make sure you mention it abundantly and don't try to mislead in any way. Use a simple clear use of colors, if possible, no colors at all. And eliminate chart chunk. What is chart chunk? Chart chunks, unnecessary information, which nobody needs and nobody should include in the graph. 3 are listed, flagging this for the exam. That's like quite a common question. Okay, so no Moireva operations, crits and ducks. Moireva operations are the patterns in those graphs and in those bars, which literally there's no reason to do that. Crits is that in the background, which should serve as kind of a reference, but you shouldn't do those. Only use like big reference lines, that's fine, but not these tiny little crits. It's just misleading. And ducks, this is a duck. Don't do ducks. Good. Then we have computer-generated graphing problems, and this is the problem why this got so common to include that stuff, because they have defaults that just include them by default. And really go the extra miles. You make a graph, deactivate them, take them out. Don't go back to the defaults. Yes.
Going on Excel, would that happen?
With some graphs, it happens, yeah. Just like, yeah, but just like if you do a bar graph, it may be filled with color. You don't need to fill it with color. There's no reason to fill it with color. Yeah, it's Excel is not too terrible, but there are some that are a bit more terrible. You will remember my words once you get across them. So there are some that show really like graphs that are not nice. R, No bias there, has the most beautiful graph. Of course. Okay, good. Okay, chart chunk, we have interactive graphing. That's actually pretty cool. You have nowadays, you have software and various applications that can make interactive graphs, where you basically, you have that graph in front of you and you can turn it, you can make it three-dimensional and you can turn it, look at it from all angles, you can deactivate some certain parts of it. So it's really an interactive graph. You will look at, you will only look at the data you want to look at. Then you have the geographic information system, the GIS software. So there's super expensive data, but then there's also open source software that allows for that. So this basically allows you to query publicly accessible information on maps, on topological information, and on information that has been made public, like risk of deaths, mortality data, heat data from the NOAA database. So there's so much data out there that can be queried. So those of you who are further in their academic career and you want to go into, I don't know, to a master, to a PhD, do inform yourself of publicly accessible data. You get so much absolutely amazing data out there, which is just to be downloaded with one click. If worse comes to worse, you shoot one email or you fill out one request form. You get absolutely fabulous data that is free of charge, just there for you to analyze. It's spectacular, really great. And this is GIS, the GIS systems. So there's definitely a lot of progress in that regard, and a lot of information that you can easily display in a very sophisticated way. You have clinical applications. In my world, iPads are on the foremarch. So they basically have iPads where you have like business BI tools, where basically you can look into the history of a patient by just swiping back into his lab values over the last 25 years. So it's great what is happening. Clinical applications are that. Word clouds, basically, that would be something where you have like the occurrence of words within a text. And you basically have like the most commonly occurring one is like bolder, fatter, more solidly colored, larger in font size. So there are various ways how to do this word clouds. They're useful for some certain occurrences, but they're not overly informative. But there's a new nice way to depict data. And then you have, lastly, you have a so-called bubble graph. That's a multivariable graph where you basically have a lot of independent information packed into one graph. Gets more and more popular now in various contexts. When you look at this graph, for example, you have here on the y-axis, you have positive emotions. On the x-axis, you have self-reported health. Better self-reported health causes more positive emotions. Yeah, I could see that. So countries with less positive self-reported health have less positive emotions. The better the health, the better the emotions. And then you have, in addition to that, you have the color coding, and they didn't put the legend in. The color code means happiness. So this is with data from the happiness report, which we'll analyze, I believe, on Wednesday. So this data from the happiness reports basically shows the happiness, the self-reported happiness in the population as a color code. So people that are have better health, have more positive emotions on the y-axis, and they have more happiness. That's why the color is lighter. Less self-reported health, less positive emotions, and the darker the color, the worse the happiness. So as we have learned, this is a positive relationship, which seems fairly linear. Okay, then you have, the size of the bubble indicates the size of the population. So that's the fourth variable in there. The fifth variable is the nominal variable of the name, which is only shown for a few selected countries. So with all these multivariable and kind of or should I say more advanced graphing methods, one point always need to be kept in mind. The more you aggregate your data, the more information you conceal. That's why I'm a big fan of scatter plots, because if you show data, so you can show these two data points with these two graphs. Which one has more information? This one, because it shows the variability, it shows the individual data point. So this is definitely one of the downsides. There are some ways to add variability information on a bar graph. There are combined graphs. There are various ways how to deal with that. But basically, it's important to keep in mind that you need to not only show central tendency, like means or medians, you also need to show the variability and preferably show the individual data point. Lastly, we have a violin plot that becomes increasingly popular now for very good reasons, and I'm a big fan of them because they show you a lot of information. They show you in here something that is labeled a box whisker plot. A box whisker plot basically has a lot of information in there. So the white point in here is the so-called middle score. Everything less than this middle score that's 50% of the data. It splits the data in half. 50% of the data is below that middle score, 50% is above. We will discuss this on Wednesday. In addition to that, you have from the white points to the lower end of the box. So usually the boxes are a little bigger, but to the lower end of the thick of the box, you have 25% of the data. So you have from that middle score to this, you have 25% of data. You have from the middle score to this upper point, you have 25% of data. In total, you have from that point to that point, you have 50% of all your data. And that is the so-called interquartile range. We will discuss that on Wednesday. From this point to this point, it's 1.5 times this interquartile range. But more about that on Wednesday. In addition to that, the violin plot shows a frequency distribution of the data, and it shows you how the data distributes. It shows you where the bulk of the data is. This is where the curve basically is highest, and it shows you the outlier. So this would be a negatively skewed distribution. No, I was sorry, positively skewed distribution, because the tail tells the tail, and the tails points to higher values. That's positively skewed. You just gotta kind of tilt it. Good. That's all I had for today. Any questions? If not, have a nice evening.
Thank you.
Thank you. Yeah.
Yeah.